Hi, in this video I will be showing you problem number 21 of chapter 11 section 3. Determine whether the series is convergent or divergent. Sigma n varying from 2 through infinity 5 over n times ln n. Notice that in this series n starts at 2 because if you plug in n equal to 1 here, because of ln 1 the denominator would become 0, so the series starts at 2. As the problem doesn't have information about what test need to be applied here, we can start off with the test for divergence, which is the easiest of all the tests. So if limit is n approaching infinity an is not equal to 0, then sigma an would diverge. So let's consider limit as n approaching infinity of an, which will be limit as n approaching infinity 5 over ln n. N approaching infinity, so n is large here, ln n would also be large, so 5 over infinity, this would be 0. So test for divergence in this case fails. So we have to apply only another test. Right now we can try the integral test, which we have done in this section. Integral test says f is continuous positive decreasing on 1 through infinity, and let an be equal to fn. Then the improper integral 1 through infinity fx dx is convergent, then sigma an would also be convergent. And if the improper integral 1 through infinity fx dx is divergent, then the series would also be divergent. In other words, the behavior of the improper integral determines the behavior of the series. So for that we need to establish that f is continuous positive and decreasing on 1 through infinity. Even though the problem says 1 through infinity, the requirement of the test, but it only needs to be proved that f is continuous positive decreasing eventually. So it could be 2 through infinity or any the starting point of this interval can be anything. So we have to only show that the series is eventually decreasing. The function is eventually decreasing. So also note in the problem we have 2 through infinity. So it is enough if we consider the relating function and then prove the decreasing nature of the function on the interval 2 through infinity in this particular problem. So consider the relating function f of x, which is 5 over x times ln x. So in the series, we change the n to x. So that is the relating function, which is obviously continuous and positive. F of x involves x and ln x in the denominator. So as long as you avoid 1, that's when the function is undefined. The function is continuous, positive, on the interval 2 through infinity. Starting from 2, it is continuous and positive. So the other part of the requirement of the test is that the function is decreasing on 1 through infinity, or eventually it is decreasing. So for that we are going to consider the increasing decreasing test. So we are going to consider the derivative of the function, and then we are going to show f prime x is less than 0 on the interval 2 through infinity. The derivative is less than 0 on an interval, then it is decreasing on that interval. So let's consider the derivative of the function. So in order to consider the derivative of the function, it's better to write f of x as 5 times x ln x to the power negative 1. So we are taking the denominator to the numerator and taking the exponent as negative 1. So what is f prime x? F prime x would be 5 times negative 1 x ln x. We are applying the chain rule here to the power of negative 2, then times the derivative of x ln x, inner derivative. This part is the outer derivative and this part is the inner derivative of the function. So it is negative 5 over x ln x the whole power 2, positive 2, so which is x square ln x the whole square if you bring it down, then we have to take the derivative of x times ln x. For that, we have to apply the product rule. So it is x, derivative of ln x, which is 1 over x, plus ln x times derivative of x, which would be 1. In other words, it would be 1 plus ln x on top, then times negative 5 outside, divided by x squared times ln x the whole square. The denominator is positive. The denominator being a square of something, it's positive. Then 1 plus ln x is going to be positive starting from x equal to 2. So this is going to be definitely less than 0. So the whole sign depends on only on this negative number. So it's going to be less than 0 whenever x is more than or equal to 2. For x more than or equal to 2, or on the interval 2 through infinity. So as f prime x is less than 0, we have f of x is decreasing on the interval 2 through infinity. So this way we have proved all the requirements of the integral test, that it is continuous, positive, and then it is also decreasing on 2 through infinity. So in this case we are using 2 through infinity, which doesn't hurt the requirement of the test. So all the requirements are satisfied. Next step is to evaluate the integral, improper integral 2 through infinity, 5 over x times ln x dx, and if turns out to be a finite value, then we would conclude that the integral being convergent, therefore the series would be convergent. If it is divergent, if this integral turns out to be divergent or infinity, or if this limit doesn't exist, then we would conclude that the series is divergent. So we have to evaluate this integral. So just look at this integral without the limits here. So if you just consider integral 5 over x times ln x dx, we are going to apply the u sub method here. So let's assume u equal to ln x. So du would be 1 over x dx. So this integral can be written as integral. So for now, if you apply the limit 2 through infinity, this can be written as 5. Then ln x would be u below, and then the remaining part 1 over x dx would be just du. So this will be, so it's better you don't write the limits here because we are applying a different variable. So it is pretty much 5 times integral 1 over u du. So it will be 5 times ln of u, but ln of u is ln x. So coming back to our improper integral, so I just didn't apply the limit here, because if you change the value to new variable u, then you have to apply the new limit. So I didn't apply the limits before. Now I'm going to apply the limits. So I can actually say now integral 2 through infinity 5 over x times ln x dx would be integral 2 through t, and limit as t approaching infinity 5 over x times ln x dx. That's the way we do the improper integral. Now it is limit as t approaching infinity, and we found that this integral is 5 times ln of ln x between the limits 2 through t, 2 and t. So it will be limit t approaching infinity 5 times. Now if you apply the upper limit and the lower limit, it is ln of ln t for the upper limit. So it is ln of ln 2 for the lower limit. So when t approaches infinity, the first part ln of infinity will be infinity, and then ln of 2, the second part, is after all a finite value. So it is 5 times infinity minus a constant ln of 2, so which is definitely infinity. So the improper integral is one of divergent, and therefore the series is also divergent. As integral 2 through infinity, phi over x times ln x dx is divergent, the series, given series sigma an, n varying from 2 through infinity, also diverges. Hope this video helps.